Welcome students, welcome to the next session of Strength of Materials 1. So in the previous classes we have given some introductions for the stresses. Then we have completed shear force and bending moment diagrams. Later we came into the stress calculation both for the flexural stresses as well as the shear stresses. Now in the next chapter we are going for the deflection calculation for the beams, which we did in the laboratory also for the calculation of deflection for the simply supported beam and cantilever beam. Okay. Now, how the formula for the deflections are generated using some methods, we are going into this chapter. Firstly, this is the syllabus involved in deflection of the beams. So, generally we should have to give the conditions. And as we have already mentioned in the pure bending theory, bending is occurring into some circular arcs. So, in that way, the curve or the bending is appearing in the arc shape, a small circular segmental arc shape like, and that is the condition they are mentioning in that. Slope, deflection, radius of curvature, all these formulas will give, and then differential equations for the elastic curve. What is the shape of the beam while bending, that we call it as elastic curve. Okay. So, when I am applying a load like this and this beam will give the shape like this. Okay. So, this deflected beam shape we call it as elastic curve of the beam. Okay. Or when I am having a cantilever or I am applying like this. So, due to this condition, the cantilever may bend like this. So, this curve we call it as elastic curve of the beam. Okay. And the next thing is, for the calculation of deflection of the beams, we will use double integration method, Macaulay's method, and some other method we call it as moment area method. And determination of slopes, deflections for. So, the main problematic concept starts from here. Determination of slope and deflections for the cantilevers, simply supported beams, overhanging beams, which are being subjected to point loads, UDLs, uniformly varying loads, and partially uniformly distributed loads. So, generally UDL may be of full length, but up to some length also. So, such they have mentioned as partially uniformly distributed loads. So, some combination may happen. And also, due to the application of couple and also combination of all these loads. So, individually point, UDL, UVLs, couples, partial UDLs, and combination of any of these loads. So, for such a type of loading conditions, we will calculate the slope and deflection for the beams, cantilever, simply supported and overhanging. Okay, and also Morse theorem, moment area method. These also will be useful than this double integration and Macaulay's method. Including these two, we will use these two for also for calculating the slope and deflection for the simple cases. Not all these complicated cases, basic simply supported beam with point load, UDL. Like those basic cases, we will solve with the moment area method and Morse theorem. Okay. So, in this way, we will calculate or we will complete the whole syllabus. The main numerical part is involved in this loading conditions, slope deflection calculations for the different types of beams. Firstly, the first word what they have mentioned is this. So, as I am applying the load, we have already indicated it is bending into a circular arc like so. The bending is occurring into some segment or the circular arc-like structure. And then, generally, when you see anything, the deflection of beam, deflection means displacement from the original position. So, originally, the beam was like this. Okay, but due to the application of this load, it has took some new shape. But this point has reached to this level. So, the vertical displacement of the horizontal line to make the curve. This portion we call it as deflection. And that deflection here we are indicating as y. There in the formulas we have indicated as delta, right? So, the same thing, this one is y. So, the horizontal line, original shape to the new elastic curve. What is the vertical deflection or movement of the beam? That is deflection y. And then slope. Slope is equal to dy by dx. What is the slope of that particular point? So, this slope theta is equal to dy by dx. You should have to remember these conditions. Deflection is y. Differentiation of the deflection we will get slope, and then ei d square y by dx square is the bending moment answer. So, ei into multiplication of this whole ei d square y by dx square is the bending moment intersection. And then shearing force is, we have already given the relation between shear force and bending moment. Shear force F is equal to dm by dx, right? So, that's why d by dx of EI d square y by dx square. In the output we have got EI d cube y by dx cube. Okay, so the shear force F is equal to EI d cube y by dx cube. And then intensity or the rate of loading. Again we have got one more relation for the intensity of loading or the rate of loading. W is equal to dF by dx. That's why we will get EI d power 4 y by dx power 4. So deflection y, slope dy by dx, bending moment EI d square y by dx square, and then shearing force EI d cube y by dx cube, rate of loading EI d power 4 y by dx power 4. So these are the terms we will use, and you should have to remember also. They may ask us, okay, as for the short answers also, right? The next thing we are going into how we will determine the slope and deflection of the different beams. Okay, so generally for determining slope deflection for a section of the loaded beam, we may use double integration method, Macaulay's method, moment area method, and also in this moment area method only Morse theorem also will be involved. So from the Morse theorem, moment area method was evolved. So directly the method is we indicate as moment area method, because this moment area method generated from the Morse theorem. Okay, Morse theorem has given one method, that is moment area method. Okay, so the first thing is double integration method. How a loaded beam can be solved using the double integration for the calculation of slope and deflection. First we will see the condition. Okay, now in case of double integration method, the equation we will directly use is bending moment at a section is equal to EI d square y by dx square. So you should have to remember directly bending moment at a section. Do you know how to calculate bending moment at a section? Yes, in the shear force diagram and bending moment diagram chapter also we have taken shear force at a section, bending moment at a section, that we know, right? So from the bending moment at a section formula, we will equate it with bending moment at a section original basic formula, that is EI d square y by dx square. Equating the bending moment at a section from the numerical, and it is being equated to EI d square y by dx square. Equating both of the two, we will calculate the corresponding slope equation and deflection equation. How we will calculate? See that the first integration of this equation, integration means this square will be removed. So integration will give dy by dx. Yes, the first integration of this equation gives the value of dy by dx, which is slope. Similarly, the second integration of this equation gives the value of y, which is deflection. So the first integration will give slope and the next integration will give deflection. So it will be converted to dy by dx upon integration, and it will be integrated to y upon the integration. Okay, so this is the way we will develop or we will calculate slope and deflection using a double integration method. The main thing you should have to remember is, here I am using bending moment at a section is equal to EI d square y by dx square, and that I am equating it to the original bending moment at the section. Okay, now I am going into the condition, a simple loaded condition, which is our general simply supported beam with a point load at the center, so that at the load is a W and they have given, and it is having L by 2 and L by 2 on both sides. Okay, so deflection for a simply supported beam carrying a load at the center, and we are having a overall length of L, and the point load is W, and which is at L by 2 and L by 2. Firstly, for analyzing anything for the simply supported beam, our first step is calculation of the support reactions. How we will calculate the support reactions? We will calculate using sigma V is equal to 0, sigma MA is equal to 0. Summation of all the moments about A is equal to 0 and sigma V is equal to 0. Using these two equations, I can evaluate the VA and VB, or when the loading is symmetrical. So how the loading will be symmetrical? When you see from the center line, on the left hand side segment and the right hand side segment should be mirror image. Like the same symmetry should be maintained when we are seeing the left segment on the right segment. Yes, here also the same symmetry is maintained. That's why the total load is divided half to the left reaction, half to the right reaction. As the loading is symmetrical for the left as well as for the right, the total load will be distributed half to the left support, half to the right support. That's why the total W is shifted W by 2 and W by 2 with the distances of L by 2 and L by 2. So this can be indicated as RA is equal to RB is equal to W by 2. So in this way, I am considering a simply supported beam AB of length L is carrying a point W at the center of the beam as shown in the figure. Just now only we have observed. Now, as the load is symmetrically applied, the reactions RA and RB will be equal. Yes, as the load is symmetrical. That's why the values are equal. Also, the maximum deflection is occurring at the center. Why it is happening like so? So, when you observe anything, it is completely symmetrically spread over the entire length. And when you keep some load over, that, and it is causing the deflection at the highest value of deflection will be at the center only. This is the point. So, this is our loading structure and we have got this condition. And at the center where the point load is indicated at that position, I have indicated the deflection answer as YC. Y suffix C. Deflection at C point. Reaction at A. Reaction at B. Similarly, deflection at C. Okay. Now, those deflections, reactions RA is equal to RB is equal to W by 2 and consider any section at a distance X from A. So, I am considering any section at a distance X from A. The bending moment at the section is given by. See here, when I am considering any section at a distance X from A, the bending moment at X is equal to, bending moment at a section X is equal to a summation of all the left hand side moments or summation of all the right hand side moments. That's why this is RA into X, which is a sagging like condition. That's it. Any other force is there? No, only this force is there. Okay. Thus, Mx is equal to RA into X, and RA we have got it as W by 2. So that's why W by 2 into X. Plus sign is indicating the bending moment on the left of the section is positive. Yes, it is causing sagging type moment on the left of the section. That's why it is positive. Now, but the bending moment at any section is also given by the equation. Yes, we already know one more equation for the bending moment at any section, that is bending moment at any section is equal to EI d square y by dx square. Yes, that is EI d square y by dx square. What it is? That is M answer only. So, M is equal to EI d square y by dx square, and but here I have got M is equal to RA into X, which is plus W by 2 into X. So, what I can say, these two should be equal. Yes, the next step, equating the both of the bending moment values, EI d square by dx square is equal to plus W by 2 into X, and with this equation, EI d square y by dx square is equal to W by 2 into X, and integrating that equation, we have got EI dy by dx, which is equal to W by 2 into X square by 2 plus C1, where the C1 is integration constant. Okay, and the value is obtained from the boundary conditions. Generally, this integration constant C1, whatever is the integration constant I am observing, that integration constant I can evaluate from the boundary conditions. Boundary condition means what are the limits I am having. Yes, when I am at the support point, there is no deflection. When I am at the center point, the deflection is maximum. Again, when I am at the last support, again there is no deflection. So, in this way, some known conditions were there. So, those are the limits for the boundary. So, those boundary conditions we can evaluate. Okay. So, C1 is the constant of integration and the value is obtained from the boundary conditions, and the boundary conditions are that at X is equal to L by 2, the slope dy by dx is equal to 0. Why it is happening? Just now only we have mentioned at the center. Okay. At C, YC is maximum. When anything is becoming a maximum, its derivative at that level is equal to 0. As Y is Y maximum at C, that's why dy by dx at C is equal to 0. This is the basic mathematical condition. When any function is becoming a maximum, at some point and its derivative at that point will be equal to 0. Yes, when any function is becoming maximum at a point and its derivative will be equal to 0 at that point. So that is dy by dx. Okay, so as x is equal to L by 2, slope dy by dx is equal to 0. As the maximum deflection is at the center, hence the slope at the center will be equal to 0. And substituting the boundary conditions in the above equation, just now only we have got an equation from the first integration process. Ei d square by dx square is equated to bending moment. Now, after integration we have got Ei dy by dx and some integration constant. Now, I am substituting in the boundary conditions. So, that is equal to, from the boundary condition x is equal to L by 2 and substituting there, what I should have to substitute in the equation, x is equal to L by 2 and dy by dx is equal to 0. These two things only I should have to substitute. Yes, x is equal to L by 2 and dy by dx is equal to 0. We have substituted and we have got C1 is equal to minus WL square by 16. Yes, C1, the integration constant we have got minus WL square by 16. So this is the integration constant we have got. And then after substituting the C1 value in the above Ei dy by dx equation, we have got Ei dy by dx is equal to Wx square by 4 minus WL square by 16. Once, whenever the value or whatever the value of x you substitute, from this equation, you can evaluate the corresponding point's slope. So, the above equation is known as the slope equation. Why? We can find the slope at any point on the beam by substituting the value of x in the equation. Okay, and the slope is becoming maximum at A, which is x is equal to 0, and also it is maximum at B, which is x is equal to L. Okay, the slope is maximum at A. Why it is maximum at A? Because from the equation x is equal to 0, the dy by dx will come, and that too in the negative manner. What it is indicating? So, when you see a protractor or the angle calculation, when you go along in this way, the values will be considered positive. Or when you go for the angle in this way, it will be considered negative. Here also the same thing happening, as the beam is bending like this and the slope is coming like this. So, at point A, that is negative values highest. That's why the slope is maximum. Similarly, here also, as it is taking in this way, this one is theta B. So, from slope equation, we can evaluate that part. Okay. So, in this way, we can evaluate. The next thing is substituting x locations, boundary conditions and calculating the slope at A. Ei dy by dx at x is equal to 0 and dy by dx corresponding to A. Okay, dy by dx at A, w by 4 into 0 minus WL square by 16, as dy by dx at A is indicated as slope at A, and this is equal to theta A, and theta A is equal to minus WL square by 16 EI. Yes, minus WL square by 16 EI is the slope at A. Similarly for B also, slope at B is minus WL square by 16 EI. Okay, in this way, from the slope equation we have evaluated slope at A, slope at B, and the integration constant is also generated from the boundary condition only. What is the boundary condition? At the center line, the deflection is maximum and the corresponding slope is equal to 0, because y is becoming y maximum and the corresponding dy by dx is equal to 0. Extreme limits boundary condition. And finally, we have got the slope answers. Later, using the first condition, we should have to calculate the deflection. Again, I am going into the main equation, Ei dy by dx minus wx square by 4 and wl square by 12. Okay, minus WL square by 16. Okay. So this is the slope equation. Again, after integrating this equation, what will come? Deflection equation will come. Yes, Ei into y is equal to w by 4 into x cube by 3 minus wl square by 16 into x plus c2. That equation we have written here. Ei into y is equal to w by 4 into x cube by 3 minus WL square by 16 into x plus C2. Again the C2, the integration constant is evaluated from the non-boundary conditions. What are the non-boundary conditions for the deflection? At the support point there is no deflection. As the same thing is only we are doing here. Okay, where C2 is another constant of integration. At A, x is equal to 0, the deflection y is also equal to 0. Now substituting the equation in the part, EI into 0 is equal to substituting 0 wherever x is happening. So we have got C2 is equal to 0. Now substituting this C2 in the above equation, we will get the corresponding deflection equation. EI into y is equal to Wx cube by 12 minus WL square x by 16. So this is the deflection equation. Again, what it gives, whatever the x value, whatever the positional value of distance you are substituting, the corresponding points vertical deflection, this equation will give. Okay, so the above equation is known as the deflection equation, and we can find the deflection at any point on the beam by substituting the value of x. The deflection is a maximum at the point C where x is equal to L by 2, and just now we have said whatever the x you substitute, the corresponding y, nothing but deflection will come out from the equation. From deflection equation, right? Right? So this is my equation and I can get these values. Okay, we can get these values. So I have used a boundary condition and evaluated. And like the previous, at A point and at B point I have calculated the slopes, and at the center point I have mentioned the slope is 0. Now I am considering at A point and at B point deflections are 0, and I am calculating what is the deflection at the C point. So where the C is located, from the left hand side it is at L by 2 distance. That means it is at x is equal to L by 2. So at x is equal to L by 2 distance, the corresponding deflection is indicated as yc. Now substituting in the above equation, we have got, so the above equation is helping us where x is equal to L by 2 and substituting, and y is represented to yc for C point. And substituting the boundary condition, x is equal to L by 2 and y is equal to yc in deflection equation. So the deflection equation will help us to calculate what is this yc answer. Yes, EI into yc is equal to W by 12 into L by 2 into whole cube, L by 2 whole cube, and WL square by 16 into L by 2. Wherever the x is there, the corresponding x answer I am substituting. Wherever the y is there, y is corresponding the substitution I am doing. Okay, then yc finally we have got it as minus WL cube by 48 EI. Minus WL cube by 48 EI. What it is indicating? That is indicating as the deflection. Generally, what we know, when this is our positive y, this is our negative y, from the basic x-axis and y-axis. This is positive x, this is negative x, right? So in the same way, now the beam line is having the deflection like this, and the deflection was in the downward direction. That's why it is minus y. So deflection in downwards, that is negatively indicated, so that the simply supported beam with a point load at the center, the corresponding deflection yc is equal to WL cube by 48 EI. So this is WL cube by 48 EI. This is the calculation for the deflection of a simply supported beam with a point load at center. And previously we have calculated slope at A and we have calculated slope at B. So these are the things we are helping. So that's why the negative sign is indicating the deflection is occurring in the downward direction. So that the downward deflection yc is equal to WL cube by 48 EI. In this way, we will calculate slope and deflection. The only thing you should have to remember is taking bending moment at a section, equating it to EI d square by dx square, and then integrating 2 times. That's why double integration. First integration will give the slope equation. Next integration will give the deflection equation. So using these 2 equations, we can calculate whatever the slope point you want or deflection value you want for the different positions on the beam. Okay. Now I am going into the next example, which is simply supported beam with UDL over entire length. Yes, the deflection of a simply supported beam with UDL over entire length. Okay. So simply I am taking a simply supported beam. Simply supported means a normal line, but it was just resting on 2 walls. A beam resting on 2 walls. Like that, the simply supported beam is there. And it is having a UDL of so intensity of the UDL is like this. And we have said already the beam will be deflected and will get mu deflected shape. Again, only for our reference I am indicating this is C and it is YC. Okay, C is simply this center of the beam. Okay, now how we will do? Again, for evaluating the deflection and slope answer using a double integration method, I should have to evaluate bending moment at a section. Being it as a simply supported beam, firstly we should have to calculate the support reactions. So that if we simply explain the loading figure in 2 statements, so we are considering a simply supported beam AB of length L carrying a UDL of W intensity per unit length over the entire length of the beam, and the reactions at A and B will be equal and half of the total load. Why it is equal and half of the total load? Because the load is symmetrical. As the load is being symmetrical over the entire length, I am considering the total load will be given half to this reaction, half to this reaction. And also, as the load is being symmetrical, the center point will have the maximum deflection. Okay. Reactions equal, maximum deflection will be occurring at the center. And W is the intensity of the load, and intensity will be converted into load form when we multiply with length. So intensity into length, we will get the corresponding load form. In the load form, half the load we will give. That's why W is the intensity and L is the length. So half of the total load will be given to first support, half of the total load will be given to the next support. So WL by 2, WL by 2. Now indicating that in the picture RE is equal to WL by 2, RV is equal to WL by 2. And we have said in double integration method, we should have to remember the formula, that is bending moment at any section is equal to EI d square by dx square. But originally in this section, what is the bending moment at a section? As the load is not at all varying, I am considering only one section, so I am taking this answer. So bending moment at any section x from the left hand side at a distance x from the left side and indicated as shown in the figure. Now the bending moment at the section is equal to, so mx at this section is equal to summation of all the left hand side moments or summation of all the right hand side moments. So I am taking here, so which is RA into x. That too it is positive. See here it is causing the sagging type moment, and then there is a negative moment of minus W into x, and it is acting at x by 2. Already we have done so many numericals for the UDLs. As x is the length of the UDL, at the center of that UDL there will be application of the load. So W is the intensity of the UDL, so W into x by 2 is the loading application multiplication. So in this way the mx will come. Now what we should have to do? From the double integration method, this bending moment at a section is equal to EI d square by dx square. Yes, this equation will be equated to EI d square by dx square, and indicating that Rx minus Wx square by 2, and R is WL by 2 into x minus Wx square by 2, and which is equated to EI d square by dx square. Yes, EI d square by dx square is equal to WL x by 2 minus Wx square by 2. And in the double integration method, in the name itself it is saying with 2 times integration you can calculate slope and deflection. The first integration will give the slope equation. The second integration will give the deflection equation. The first integration EI dy by dx, we will get the corresponding integrations WL by 2 into x square by 2 minus w by 2 into x cube by 3 and plus c1. Don't forget the integration constant which you have to compulsorily mention because different variables were there. That's why integration constant will come. And c1 is being the integration constant and that c1 will be evaluated from the boundary conditions. Again, we will do the complete next integration also. At a time, we will evaluate c1 and c2. Okay. No need to involve in between. At a time, we can complete the integration process and then we can substitute the boundary conditions. So, the next integration we are doing is ei into y. So, the next deflection equation will come. So, that ei into y is equal to wl by 4 into x cube by 3 minus w by 6 into x power 4 by 4 plus c1x plus c2. So, here we have got first boundary conditions from the first step, second boundary condition from the second step. That's why c1, c2. Okay. Now, the c2 is another integration constant. These two constants of integration such as c1 and c2 will be obtained from the known boundary conditions we are having. Those boundary conditions are, what are the boundary conditions I am having? I know at the center the deflection is maximum. As the deflection is maximum, its derivative is equal to 0 at the center. That's why at x is equal to L by 2, dy by dx is equal to 0. Either in that way we can develop, or from this equation using two boundary conditions also we can evaluate. So what are the boundary conditions? At x is equal to 0, y is equal to 0. On the left hand side there is no deflection. Similarly, at x is equal to L also, y is equal to 0. So using these two boundary conditions also you can develop. So firstly at x is equal to 0 and y is equal to 0, indicating that first in the deflection equation. Using two boundary conditions of deflection equation only. Okay, I am using two boundary conditions of deflection equation only. I am not touching the slope equation. Now substituting that we have got c2 is equal to 0. After substituting that c2 is equal to 0 in this, again we have got one more equation. That equation will be equal to 0 at x is equal to L. So at the other end of the simply supported beam also there is no deflection. That's why substituting the secondary boundary condition, which is x is equal to L and y is equal to 0. Sorry, x is equal to L and the corresponding y is equal to 0 in the equation 2. We get 0 is equal to wl by 4 into L cube by 3 minus wl power 4 by 4 minus w by 6 into L power 4 by 4 plus c1 into L. As it is the first Bendigo-Data section, first integration, second integration. This is second integration equation only. I am using two boundary conditions. First one is x is equal to 0, y is equal to 0. Next one is x is equal to L, y is equal to 0. So from the first boundary condition I have got one answer, and the next boundary condition is helping me to evaluate the next integration constant, that is c1, and we have got the c1 answer like this, and substituting in the slope equation and deflection equation as it is. So from the slope equation I can write like this: wl by 4 into x square minus w by 6 into x cube minus wl cube by 24. See here, minus wl cube by 24 is the final output of c1 constant we have got, and c2 I have got as 0. Now from the next condition, from the deflection equation substituting c1 and c2 at a time, I have got ei into y is equal to wl by 12 x cube minus w by 24 x power 4 wl cube by 24 x. So in this way we have got slope equation and deflection equation. What these two equations will give? Whenever the point you are substituting the x corresponding positions, and I can calculate the corresponding deflection, and I can calculate the slope of that particular point on the beam. Yes, the equation 3 is known as the slope equation, and the equation 4 we can calculate known as the deflection equation. And the slope equation is helping us by substituting the x and getting the different values of corresponding slope points, and also for the deflection also the same thing. When x is equal to 0, whatever the location you put, corresponding locations the deflection will be evaluated from this step. Now going into the next condition. Yes, for some special points we will calculate slope answers and also we will calculate the deflection answers. Yes, I am calculating the slope at the supports. So slope at the supports means at x is equal to 0, that dy by dx, how much? And I am indicating dy by dx as theta a. Slope at a. Similarly at b, slope at b. Okay. So at x is equal to 0, dy by dx is indicated as theta a, and x is equal to L, dy by dx is indicated as theta b. So substituting those boundary conditions, we will evaluate with x is equal to 0, dy by dx, which is theta a, and we have got the corresponding answer as wl square by 24a. Simply substituting from the slope equation. Yes, the slope equation will help us evaluating theta a. Similarly, the condition with the complete right hand with x is equal to L and dy by dx is equal to theta b. So, using the next boundary condition, the corresponding slope will be evaluated. In this way, we are evaluating our slopes. And the next step, we are calculating the deflection. As the deflection is occurring at the center which is being maximum, where it is happening at x is equal to L by 2 point. At x is equal to L by 2, from the deflection equation, substituting the boundary conditions. So, with x I have replaced as L by 2 and y I have replaced as yc. From the deflection equation, substituting these two answers, and I have got the deflection answer as 5w L power 4 by 384a. Again the same thing how we have mentioned when I am measuring towards positive y, the corresponding answer will be positive y. But here the deflection is occurring in the negative y sign. That's why I have got that yc is equal to minus 5w L power 4 by 384 ei. That's why negative indicating downward direction. Simply I can indicate yc is equal to 5w L power 4 by 384 ei, which is the maximum deflection occurring at the center in the downward direction. Okay, in this way we are evaluating slopes and deflections at different points on the beams using double integration method. In the next class we are going into McLeod's method.